So we are dealing with the 12th problem in this series. The problem number is 3.12. The problem is stating a thin non-conducting ring of radius r has a linear charge density lambda equals lambda naught cos phi, where lambda naught is a constant and phi is the azimuthal angle. Find the magnitude of the electric field strength at the center of the ring and on the axis of the ring as a function of the distance, and then investigate the obtained function for x greater than r. So if we begin this problem, we need to first of all understand the orientation of charge. To understand the orientation of charge, we are considering a ring like this. So when we are considering a ring like this, I am also drawing the quadrant aspect over here. So we have an arrangement like this, and now the problem is stating that the charge is varying as lambda equals lambda naught cos phi, and about the angle phi, it is said that the phi is the azimuthal angle. So if we understand this aspect, so we can say that over here at this point the angle phi is equal to 0 degree. For cos 0 the value is maximum, so the value of the positive charge is maximum here at this point. Right at the opposite end the value will be 180 degree and the value will be minimum, that is negative greatest charge possible here. For 90 degree value at this point the value will be 0. For 90 degree, that is, or 270 degree at this point the value will again be 0, and the variation of charge will take place as per the value of cos theta. So the value of charge will go on diminishing till it reaches the point and becomes 0. Similarly, the value on this side also will be diminishing till it diminishes to 0 here. As far as the negative charge aspect is concerned, the negative charge value will also decrease in magnitude and become 0. The negative charge value will also decrease in value and will become 0 gradually. So this is the first thing that we need to understand whenever we are understanding this particular charge configuration which this problem is stating us to calculate. So this is the first thing to understand. Now the next part which we want to understand is that it is asking us to calculate electric field at the center of this non-conducting ring. To calculate electric field at the center of this non-conducting ring, we are selecting a patch of charge which is at an angle phi from here, making d phi. It is also convenient for us to understand, after understanding the orientation of this charge, that the electric field value at this point, which is the center, will be directed only towards the negative x direction. This is going to be the electric field at the center. It is because the electric field which will be created by the upper charges will have a component like this, which we have considered here also, that this will definitely have a component like this dE in this direction, but the lower charges will also have a magnitude dE in this direction, and the y component of both the system will cancel each other. So we will only be left with the electric field which is directed along this side. And also it is convenient for us to understand that this system of charge is such that every positive charge on this side is having a negative counterpart on the other side. So we can also consider it as a big dipole, which we will use in the next part of the problem. So over here, if I consider the electric field due to the elemental charge over here, which we consider as dE, then if this angle is phi, then this component will be equal to dE cos phi, and the other component will be dE sin phi. The value of dE sin phi will eventually turn out to be 0. So if we are calculating electric field at the center, so the first thing that we have is the length of this part. So length of this part is equals r d phi, and the charge dq is equal to lambda naught r cos phi d phi. So therefore electric field at the center is equal to dE cos phi. Now to calculate this value dE, we use k, that is 1 upon 4 pi epsilon naught small charge dq lambda naught r cos phi d phi by r square, and since it is a cos component we are putting cos square phi. So this is the value that we have. Now it is again very important for us to understand that we are calculating this using integral method, and we integrate for the entire length of the non-conducting ring, that is from 0 to 2 pi angle. So on solving, we obtain electric field at the center as lambda naught upon 4 pi epsilon naught r integration of cos square phi d phi 0 to 2 pi. So we can solve this integration by substituting cos square theta or cos square phi as cos 2 theta plus 1 by 2 and then solving it out. So on solving we obtain lambda naught upon 4 epsilon naught r. So electric field at the center of this non-conducting ring is equal to lambda naught upon 4 epsilon naught r. So this is the first part of the problem which we have covered. Now in the second part, the problem is asking us to calculate the electric field on the axis of the ring as a function of the distance x from the center. Now to understand this part, I am again drawing the orientation of the charge. So we are again considering the orientation of this charge, which I explained earlier also, that we have a ring of charge, and this ring of charge is having charge distributed such that each positive counterpart over here is having a negative counterpart. Each positive counterpart here is having a negative counterpart, and gradually the value is decreasing like this and diminishing to 0. Similarly, value over here is decreasing like this and reducing to 0. The same arrangement is on this side. So each positive charge on this side is having another negative charge on the other side. So this system is behaving like a dipole. So what we are doing is we are trying to calculate the dipole moment of this system. So to calculate the dipole moment of this system, we are again considering the same aspect, that at an angle phi we select a small elemental part d phi, and for the positive charge over here we will have a negative charge on the other side, which is this charge, and the separation between them can be taken as 2r cos phi. So 2r cos phi is the separation between the positive charge and the negative charge, and therefore the dipole moment for the given charge system so we can consider it as dp equals charge, that is lambda naught r cos phi d phi, and multiply by separation between the charge, that is 2r cos phi. And if we integrate this value, so we will get the value of dipole moment, that is 2 lambda naught r square integration of cos square phi d phi, and the value, since we started from here, so we are integrating it from minus pi by 2 to plus pi by 2. So the net value of dipole moment can be written as 2 lambda naught r square, and we are writing cos square phi as cos 2 phi plus 1 by 2, that is we can write it as half d phi plus cos 2 phi by 2 d phi, and we are integrating both aspects from minus pi by 2 to plus pi by 2, minus pi by 2 to plus pi by 2. So this is the integral that we have, and therefore the net value of dipole moment that we calculate is turning out to be lambda naught r square pi. So this is the value of the net dipole moment of the system. Now the question reduces itself to the electric field due to the dipole, and electric field due to dipole at a distance x can be written as kp by x square plus r square to the power 3 by 2, and therefore the final answer is going to look like 1 upon 4 pi epsilon naught lambda naught r square pi by x square plus r square to the power 3 by 2, and it is equal to lambda naught r square upon 4 epsilon naught x square plus r square to the power 3 by 2. So this is the second part of the problem which this question is actually asking us to calculate, and in the last part it is asking us to calculate for x greater than r. So we increase the value of x greater than r, then we can also deduce the result r square epsilon naught upon 4 epsilon naught x cube. So over here I am writing for x greater than r, E is turning out to be lambda naught r square by 4 epsilon naught x cube. So after that expression we can write this. So this is also an integral part of the answer which the question is asking us to calculate. So the most important part for this problem is to understand the orientation of charge. Once we are comfortable with the orientation of charge, then the entire problem can be solved in a different aspect altogether. So this is how we deal with the problem 3.12. It is a understanding and a nice problem, one of the few fantastic problem that we have.